So yesterday and the day before, we worked on force diagrams and working with more force diagrams. Today, we're going to talk about how to calculate forces using the force diagrams. So there's a couple of things that we have to keep track of. The first thing that we have to keep track of is the formula for the gravitational force. And I'm going to tell you that the formula for the gravitational force is the force of gravity is equal to the mass of gravity, or mass times the gravitational constant. Okay? Now, the gravitational constant is the same value all of the time. It's 9.8 newtons per kilogram. So that's always the value of gravity in this class. So what that means to you and to me is that when we go ahead and we calculate something and we use the gravitational constant, that lowercase g, we're always going to insert 9.8, okay? Now, the units for force of gravity and the units for all forces are the newtons.
So Fg is the formula for force of, Fg is force of gravity.
Yes.
Oh yeah, I did it.
So is the newtons, capital N, and mass in this case has to be in kilograms. Now, if I happen to give you a mass in grams, you should be able to convert it to kilograms, and I'm going to show you how to do that right here. So mass in grams, I would multiply by 1 kilogram over 1,000 grams, which will give me mass in kilograms. An example of that might be something like 37 grams, 1 kilogram over 1,000 grams would equal 0.037 kilograms. Not quite. It's just doing a little bit of math. A little bit of math. Sometimes we would put this over 1. That might make you feel a little bit better about yourself, but that's how we convert from grams to kilograms. Okay? So far, so good. Any questions?
Did you get it? Can you see it? Do you need to move up, or are you okay? You can always look at mine too if you miss them.
So that's calculating the force of gravity. Other than that, you're not going to do a lot of calculating of forces without doing the force of gravity. So the force of gravity is going to kind of always be part of the deal. Now, moving forward, can we go ahead?
No.
Okay.
It literally means.
For example, if we were going to calculate the force of gravity on a 2 kilogram pass car, this guy right here,
I don't think the people look can see it.
it doesn't matter, okay? So we are going to first of all use our formula. So we're going to have force of gravity is equal to mass times the gravitational constant, which, when we substitute our values in, force of gravity is equal to 2 kilograms times the gravitational constant, which in this case, we just said was 9.8 newtons per kilogram. So when I do the math on that, I get a force of gravity equal to 19.6 newtons. Ka-chow.
Use a different word.
Oh, I like ka-chow.
It's not all about you, Mr. Sensei.
Considering the fact that we are rapidly approaching the summer season, in which case we are going to pretty much bypass spring and eventually just end with summer, but there'll only be like 3 weeks of summer.
Correct.
Because it's going to be like this weather all of May and June and July, and somewhere around August 30th, we'll get like 90-degree weather.
Not me.
What do you mean, not you? Oh, well, in any case, it's just making me think about watermelons, because I do love watermelon.
That's the best one in the world. Okay, you have to explain all that just to say watermelon.
I wanted to figure out
He's setting the stage.
what the force of gravity or what the mass of a 89.2 Newton watermelon is. That's a pretty solid watermelon. So what I'm gonna do is I'm gonna take the force of gravity is equal to mass times the gravitational constant. And I'm told that I have newtons, so I'm gonna throw that over here. 89.2 newtons is gonna equal mass, which I wanna figure out, times the gravitational constant, which is 9.8 newtons per kilogram. Well, I mean, units are kind of important, because as far as I'm concerned, when you just write numbers in a science class, it's
It's numbers.
no, it's just numbers. They don't mean anything. But it's like they're naked. You know what I mean? And like I feel like all numbers like have some value to them. You don't just walk around and be like 7. It's like $7 or 7 pennies or 7 clutches or
It's seven, this.
it's dollars though.
No.
Right.
Say seven.
Yeah, your total's like 782, which has value to it, right? But what I'm saying is that like to a scientist like myself, if you just write 82.9, it looks like a naked number, which is the equivalent to I have the same reaction that you would have if you happened to walk in and see one of your parents standing there naked.
Whoa!
Nobody wants to see that.
Are you put that on the video?
It's on the video. Nobody wants to see that. But what I'm saying is that when you just write a number naked, I have that same aversion that you would have thinking about potentially seeing.
Yeah, but that's a totally different. like,
Oh, no.
concept.
No, it's not to me.
It doesn't matter.
Pure
You
knowledge here.
feel like.
But I'm saying in this case, it
Why
would
we talk about naked
trying to
parents?
find grams.
So 9.8 newtons per kilogram divided to both sides, 9.8 newtons per kilogram cancels out, and it leaves me with a total mass somewhere in the ballpark of 9.1 kilograms. And actually, could you not sing because I'm trying to lecture here? It is your bad. Now, what the other thing is that 9.1 kilograms, so is equal to like, well, they say that 1 kilogram is like 2.2 pounds. So this is like an 18 pound watermelon. That's a giant watermelon.
18 pounds.
Guinness Book.
We should eat watermelon last day of school.
We should go to the next slide. Has everybody written this down? We
We
good?
can do the egg
Go
drop
up there.
challenge.
We good?
3 big watermelons to drop.
Can I move on?
Slow motion.
It's fine. Ka-chow!
You can watch the video.
Wait, sorry, I gotta go back. Now, a quantitative, what?
Can you go back?
Why?
Is it kilo?
Okay, now,
Thank you.
you're welcome. Quantitative force diagrams are designed to quantitatively and draw an accurate force diagram for a 2 kilogram pass car sitting motionless on a track. So here we have this guy right here. He's 2 kilograms, he's sitting motionless, okay? So here's my cart. Pass car. See what I did there? Pass car. NASCAR. Get your belt buckle. So in any case, we're told that this is a 2 kilogram pass car. So in this case, because we previously calculated, remember we said force of gravity is equal to mass times gravitational constant. We said the force of gravity is equal to 2 kilograms times 9.8 newtons per kilogram. And so we said that the force of gravity of this particular car was 19.6 newtons. Remember that from the slide before? Yeah? Okay. So what I'm going to do here is I'm going to draw the force of gravity. So the force of gravity in this case goes, okay? And I have to identify that it's the force of gravity on the car by the earth. Okay? Force of gravity on the car by the earth. And then we have to deal with the fact that there is a motionless car, so it's meaning, and there's also a force of the track pushing up on the car, which we refer to as a normal force. So I'm going to draw, so this is the force, the normal force acting on the car by the track. And if the force of gravity was equal to 19.6 newtons, the
car and what?
track. The normal force also has to be equal to 19.6 newtons. And note the congruency marks are the same number of congruency marks so that we can show that the force of the gravity and the normal force are the same. So far, so good with that. May I move on? We still drawing? Well,
You should just say Jill's name.
so now we're going to add some forces. And so this becomes a little bit more complicated because there might be a little bit math involved. So let's talk about the math. Okay, so here we have Jack and Jill, my friend, Jack, and his fiancée, Jill, okay?
I thought they were sister and brother when I first watched them.
Siblings?
I don't know, no, these are my friend, Jack, and his fiancée, Jill. He grew up,
Two generic names.
he grew up wishing that he would meet someone named Jill so they could have the Jack and Jill lifestyle. So yeah, so they oftentimes go up a hill and get a pail of water, and then they tumble down the hill. That's what they do in their free time.
Got a pail of water, tumbled down the hill. Is that how it goes?
No, Jack and Jill went up a hill, each with a bucket of water. Jack fell down, broke his crown. Jill came tumbling after.
What is a crown?
Anyway, anywho,
Don't talk.
Jack and Jill are working together as a team. Shh, guys. They're working together as a team to move a 115 kilogram box. So Jack is pushing. So this is Jack. And Jill is pulling, okay, on a rope. So if Jack is pushing to the right, he's going to go in this general direction, and Jill is pulling to the right as well in that general direction. Now, here's the deal. Jack is pushing to the right with 150 newtons of force, and Jill is pulling to the right with 100 newtons of force. So I'm just kind of like I'm painting a picture here, people, so you guys can see what's.
Jill have like the bigger hand?
No,
That's not it. This is the rope. This is her rope,
Oh,
okay? That is her rope.
shut.
Now, here's the deal. You have to go ahead and draw a force diagram that illustrates the scenario in question. So here is where we are at. The first thing that we need to do is we need to sort of figure out what the force of gravity is on this particular box. So what I'm going to do is I'm going to use my formula. Force of gravity is equal to mass times the gravitational constant, which means that the mass of the box, we said, was 115 kilograms, and the gravitational constant is always 9.8 kilograms, or newtons per kilogram. So that tells me that Fg, when I solve for the force of gravity in this case, is going to be equal to a grand total of 1,127 newtons. So now, when I draw this force, I'm going to draw this. Okay? And I'm going to say force of gravity is the box, force of gravity applied on the box by the earth. Okay? We also have a normal force, right? So we have a normal force, which is going to cancel that out because they're going to be the same. So force normal is being applied to the box by, in this case, the ground. Okay? So far, so good with that. Now, in this case, ladies and gentlemen, if the force of gravity is equal to 1,027 newtons, we have to assume that the normal force is also 1,027 newtons. So I'm going to give a tick here and a tick here,
Precisely.
showing congruency. All right? Now, in this instance, right, I have Jack.
Jack, what's good, my dude?
All right? So Jack is pushing on the box with 150, newtons of force. So in this case, it's the applied force on the box by Jack. Okay? Now, Jill, on the other hand, is pulling with 100 newtons of force. So her force being applied is Fa on the box by Jill. All right? So far, so good with that. However, we know that these are not the same. So this and that are not the same. Does that make sense? So I drew tick marks indicating that they're not the same. Now, the issue in this case, though, is that the box is not going to move at all. And as a result of the box not moving at all, oh, that's a great color right there. So as a result of the box not moving at all, I know, that's why I like it. As a result of the box not moving at all, right, I have a force of friction being applied to the box by the ground in the opposite direction of the force being applied. So what is the total force being applied to the right in this case?
250.
Thank you. So if I said that I had 150 plus, so if I had the 150 newtons plus, plus the 100 newtons, the total force going in the right-hand direction is 250 newtons. Does that make sense? So far, so good? Okay? So that means that if the box is not moving at all, that means that the force of friction has to be 250 newtons to the left, and I'm going to give it, because it's just one force, 3, 4, I'm going to do 5, and let me explain why. Because if this set of tick marks for Jill and this set of tick marks for Jack adds up to 5 tick marks, then I'm going to do 5 going the other way to show that it's canceled. It's equal. Does that make sense? Do you follow that? Question. Question? Question? Query, quaffle, conundrum?
What?
Ka-chow! All right. Your homework then is to do the worksheet on the inside of this packet, which I don't have the packet in front of me, but it's like a 2-sider, I think.
Due Tuesday?
It is.
It's due Monday. So it's this guy right here. It's this guy and this guy. So you're doing questions 1, 2, 3, 4, 5, and donezo.
Wait, so we don't get packets, but we get extra homework?
What are you talking? That doesn't make
Hey.
sense.
Packets